Okay, we'll go on, and yes, we have another midterm scheduled for next week. I'll talk about it, I guess, on Friday, and I got to work on that myself. Okay. But anyway, it's week 6 Wednesday, and on Monday we talked about the Bayes classifier. And so just a quick recap of how the Bayes classifier works is we use Bayes' rule to figure out the probability. What we want is what's the probability that this observation belongs to a certain class, and I'm sorry, what's the probability that an observation belongs to a certain class given it has these numeric values, okay, or just these variables in x new, that this new observation, what's the probability it belongs to a certain class? We use Bayes' rules, right? Bayes' rule says if you want A given B, you can do it by finding B given A, and then multiply it by probability of A and divide by probability of B. So we're going to say what's the probability that something belongs to a class given that we have these new values? Well, it's going to be equal to what's the probability of getting those new values if we assumed it belonged to a certain class, okay? And this is going to require us to say, well, what is the probability that it's going to give these values if it belonged to class A? And what's the probability it gives us these values if it belonged to class B? Or what's the probability it produces these values if it belongs to class C, and so on and so forth. We multiply that by the probability of each of these classes, their prior probabilities before we even look at the values in here, and then we divide by a marginal probability to make sure everything adds up to 1. And so we did this for multivariate Gaussian mixture, and we said our data, the training data looks like this. Okay, so the training data comes in labeled, and we use these ellipses, these black ellipses, to generate the data. Okay, the generated data has mean 0, 0 for the blue, has mean 2, 3 for the red, and mean 2, negative 2 for the green. There's covariance between x1 and x2 in the green, but no covariance for x1 and x2 in blue, and no covariance for x1 and x2 in red. Okay, and then when you do the classifier, you don't actually know the properties that generated the distribution, so you have to estimate these things. So just using the dots that are labeled, we estimate the means and we estimate the variances. And we just use R's built-in variance function. We use R's built-in mean function, and that's good enough. And so these would be the estimated distributions based on the values we see. Okay, so based on the blue dots, this is what we estimate the mean and the variance to look like. Based on the green dots, this is what the mean and variance is estimated to be. Or I mean, these are the distributions, I guess, using these ellipses. So this is estimated off of the dots. And again, if you compare that to the known contours that we use to generate it, we see that they're similar but not exactly the same. All right. And then so we said, well, what is the value of this test case? What's the probability, classification probability for this test case? And just by looking at it, we'd say, oh yeah, this one's got to be blue. And when you do our calculations, yeah, indeed, it says it's going to be blue. Okay, no surprise. And usually, that's always a good thing to check. Is you'd say, did I create my model correctly in the computer and stuff like that? Always give it like an easy softball answer that you can say, like, this has to be blue, right? And then you run it through the thing, and then if it comes back and it says blue, it doesn't necessarily mean you have it correct. But at least like it's not obviously broken, right? If it comes back and it says it's going to be red, you'd be like, oh, okay, I must have done something wrong, right? So it's always good to just do these kind of sanity checks to just make sure your thing's working. Okay, so anyway, again, a review of Bayes' rule here, and And when we calculate this likelihood, the likelihood of the data, I could technically use the multivariate normal PDF, which has this PDF, and I can go through it, and it will give me the likelihood of getting this new test case, which is at 0, 0. What is the likelihood of getting it? If it belonged to class A, what's the likelihood of getting that observation if it belonged to class A using, X bar A and the variance A? That these are the values we estimated. And it comes back and it says it's 0.000879. Thankfully for us, there is the function multivariate normal density, and you don't have to do all of this, and you get the same exact number, 0.00879. Okay, so that's nice. And we can do the same thing. We can say, okay, well, what's the likelihood of getting that observation if it was part of class B? What's the likelihood of getting this observation as part of class C? And it comes back with these other numbers here. Okay, and then we run through the prior probabilities. In this case, we had 90 observations total, and each class had 30 observations. So our prior probabilities will just be 1/3 each. Okay, and technically these things all cancel out because I'm going to have, I'm going to multiply each value in the numerator by 1/3, and then I'm going to divide by the sum of them. And so all of these, if all of your prior probabilities are all equal, then they all cancel out. But if they're not equal, it's important to include them. So, in the denominator, we're going to have the likelihood times the prior for each of the classes. So basically, the numerator for class A plus the numerator for class B, likelihood times the prior, plus the numerator for class C, likelihood times the prior. So that goes into the denominator. Okay. And then so we do the posterior is the likelihood times the prior divided by the marginal. Okay. And we get these numbers. These things will all add up to 1. And as we expected, the probability that the observation belongs to class B, the blue group, is the highest at around 99% probability. So this is our classification, and we'd say we're 99% probability that it comes from class B. So that's the Bayes classifier. Okay, here's another test case. We could say, well, what's the probability that it belongs? What if our test case is here? So what do you guys think? Is it more likely to be red or green? It's kind of like we're not sure. All right, let's see what the thing says, okay? So we're going to say, well, what is the likelihood that red generates this point? What's the likelihood that green generates this point? We also include what's the likelihood that blue generates this point, right? This blue generating this point is very unlikely. But red and green, they look whatever. Okay, something. Okay, so again, we calculate the likelihoods using the multivariate normal density. So this is all on one slide, and it's kind of quick here. But our new test case is at 6, 2. We say, well, what's the probability of getting 6, 2 if we have this mean, which is something around 2, 3. It's not exactly that. It's something else. And the variance A. And what about these other things? Okay, we have the priors, we have the marginal, and then for each case, we do the likelihood times the prior divided by the marginal. And so it says around 79% chance of class A on 10 to the negative 9 for class B, and 20% chance for class C, okay? So around 79 and 20, 21%, something around there. So class A has the highest probability. And so it's hard to tell, but I guess it makes sense, because if you look at this, this is within the final ring, whereas it's definitely outside of the final ring for green. So makes it a little bit more likely to be A. Okay, what about this one? All right, so here I'm intentionally picking all of these edge cases, like these things on the border. All right, and then you go through the math here, and we're a lot 39 versus 61% probability. Class B is still on the order of 10 to the negative 6. So 39 versus 61. Class C, And I guess that's the split, something around there. Okay, and then if it's like right here in the middle of all of these, they're all very close to each other, around close to 30 something percent each, 31%, 36%, 33, 34%. So class B has the highest of these probabilities, but not by much. Okay, so this one's really like, we're not really sure if it's red, blue, or green. And yeah, if I think if you gave this dot to a bunch of people and said, hey, what class is it going to be? I think everybody would have a little bit of a hard time, right? It would be a bit of it. All right, so everything kind of lines up with our intuition. And so that's the Bayes classifier. And maybe I'll just pause and make sure that this all makes sense as far as how this works. Okay, great. Let me give you your first view quiz answer. First view quiz answer is D. D as in dog. D as in dog. Wait, I think. Okay, D. All right, so that's that. So let's do the same thing, except we're gonna make it naive. Okay, so I don't know if you've heard of this, the naive Bayes classifier. It's pretty much the same thing, except we have the word naive here. All right, so what makes something naive? Well, I guess a lack of life experience, but as far as our classifier goes here, we call this the naive Bayes classifier because we simplify the way we calculate our likelihood, okay? So in real life, things are complicated, right? There's like relationships between all sorts of different forces at play. And so if you want to know like what's the effect of something on something else, there's like a million factors to consider. What we're going to do with the naive Bayes classifier, okay, so if you review this, the multivariate Gaussian, this is how we calculate the density for a multivariate Gaussian. We allow for covariances in the covariance matrix. But if we said the covariance matrix is diagonal, meaning that there's no covariance between x1 and x2 or any of the x variables, then you would have a diagonal covariance matrix or a variance covariance matrix, and you could then factor it out into a product of univariate Gaussian PDFs. Okay, so that's what we're going to do. So the naive assumption is that all of the x variables are independent of each other, that you got x1 and x2 and x3 and whatever, and they're all independent, that there's no relationship between them. And that's a bad assumption, right? Because in real life, many things are related. And here we're going to just say, you know what, I'm going to just assume that they're all independent, okay? And we know that's a bad assumption. So why would we intentionally make bad assumptions, right? Why would I intentionally? I know in real life, x1 and x2 probably have some kind of covariance. x2 and x3 probably have some kind of covariance. And x1 and x3 probably have some kind of covariance. Maybe they're not strong, but to assume that they're zero, that's probably a bad assumption. So why would I intentionally use the naive assumption or the naive Bayes classifier? Well, a lot of times it's because the answer is it makes our life easier, right? When you assume things are independent, you can just multiply probabilities together. You don't have to worry about covariances, right? Like compare this, right? Now, I mean, we have a computer that can calculate this easily for us. But if I said calculate the density, the probability density for this observation in a multivariate thing, it's like a lot harder than if you just said, well, treat x1 and x2 and x3 as all independent, and you'd have these univariate things and multiply them together, right? So one thing is it makes it easier. And the other thing is, now that we're assuming all the covariances to be zero, even though that's a bad assumption, again, it makes our life easier because we don't have to estimate the covariances, okay? And in order to estimate covariances, a lot of times you need lots of data, especially if you have many variables, okay? If you have a whole bunch of variables, like if you have 10 variables, how many covariances are there? What is it? 10 choose 2? So 10 choose 2 is 10 times 9 divided by 2. I don't know. It's like 45? 45 covariances? I don't know. Something? 55? Something. Okay. Nobody knows. All right. A lot, right? You got a lot of covariance things, right? And if you have 55 or 45 covariances to estimate on how many observations do you need to get accurate estimates of these covariances? You need a lot, right? And so, and if you don't have a lot of covariances, then, I mean, if you don't have a lot of observation, then what's going to happen? You might still have covariance estimates, but now you have like a huge margin of error on those covariances, right? You have a huge standard error on these covariance estimates that are based on just a few observations and things like that. So now your model is subject to a whole bunch of stuff, okay? So instead, we're just going to make a bad assumption and say everything's 0. That makes our life easier. And we say, well, you know what? There's also limitations to our model, right? So as long as you're kind of aware of these things, of your assumptions, and whether or not these assumptions are reasonable to make will determine whether you should be using the naive Bayes classifier or not. So if you're in a situation where you know there are huge covariances between x1 and x2 and that they should not be ignored, then probably don't use the naive Bayes classifier. But if you're in situations where you'd say, there's some covariance, but it's not probably going to be super huge, maybe we can get away with it, then maybe you can get away with it, okay? And this, I always feel a little bit silly talking about these things because there is a bit of subjectiveness, and there's a lot of kind of like, you know, with statistics, it's like where the math meets the real world, right? And in the math, you have these ideal scenarios and situations, and there's only one answer, and there's only like one truth to the universe. But with statistics, you're just like, well, life's kind of hard and complicated, so let's hope we can get away with some assumptions. And that's basically what we're going to do. So all we do is we take the multivariate Gaussian, and we just turn it into a product of univariate Gaussians. And we could say this is an approximation. We're going to approximate the multivariate Gaussian with this. I guess I should do a squiggle here for approximately equal to this. Okay, so what's going to happen, if this is our original data, we'll probably be fine for the blue and the red, and the green is where we're going to be the most off, okay? So if we have x1 and x2 independent, when we estimate, what will our ellipses look like? What happens is that the major and the minor axes of the ellipses are parallel to the axes. Okay, so anyway, when we estimate the parameters for our data, okay, so again, we don't know the actual distributions that generated the data. We're going to estimate these things. We just calculate the mean of, you know, x column 1 and xb column 1, xc column 1. Technically, column means will work too, but I'm going to just do all of the variables independently. Okay, so variance 1 and standard deviation 1. We're going to just do one variable at a time. So no covariances. These are just single scalar values. And then so when I create this, these are the estimated lines, and what we see is for the green distribution, we can see this doesn't do a great job for the green distribution, which has a lot of covariance, right? Under the naive assumption, we're assuming there's no covariance. So yeah, this is what we estimate. We're basing just on the variance that we see in the x1 direction, the variance we see in the x2 direction, and we're assuming they're independent, so the major and minor axes of the ellipse are perpendicular to each other, and again, not super great. It looks okay for red and blue, because those were actually the case in our generating distribution. Okay, so compare this to when we use the multivariate thing. Again, they line up, purple and orange line up okay here, but not for the green data. Okay, but then we run it through the classifier. We put in this dot, and we say, is it likely to be blue, red, or green? And when we do this, it comes back, and it's going to tell us that it's still blue. Okay, so this is how we calculate the likelihoods. Okay, to calculate the likelihoods, we do a product of univariate normal densities. So here, I'm not using the multivariate norm. I'm just using plain old D norm, right? That we're all familiar with, D norm, and we have this. So we take for our new observation, at least variable 1, we calculate D norm using the mean of x bar 1 for class A and the standard deviation for x bar 1 for x1 for class A. And then because I've got two variables in x, I do it for the first variable, x nu 1, and then I'm going to do x nu 2. And it's a product of two D norms. So rather than one multivariate normal, it's a product of two D norms. Okay? And that's what we have. All right. Is that okay? Calculating the densities here, or the likelihoods. So we say, what's the likelihood of x1? And we do it for class A, class B, and class C. And then again, to get the marginal probability, the priors, we're all going to set to 1/3 each. The marginal is the likelihood times the prior for everything in the numerator for all three classes. And this is what we end up getting. All right, and so we get 94% class B, so highest probability here. It's not as dramatic as what we had when we had the multivariate normal. The multivariate normal said like 99.5% probability that it was class B. Now it's 94% class B. So we're still going to pick class B, but we're also off by a little bit. Okay, so this is the naive Bayes classifier. Is that right? So the biggest difference when you do naive Bayes is you're going to have a product of univariate normal densities. And I think this is your first task in the new homework assignment that was posted, is you create a naive Bayes classifier for our favorite iris data set, right? And so for the iris data set, how many variables do you have? You have 4 variables. We have 3 classes, but 4 variables. What is it? Petal length, petal width, sepal length, sepal width, okay? And so each likelihood is going to be the product, for the naive Bayes classifier, is going to be the product of 4 normal densities. So you'll do D norm, petal length, D norm, petal width, D norm, sepal length, D norm, sepal width. And you have to calculate the mean and standard deviation of each of these 4 variables for all 3 classes. So you're going to have a whole bunch, 12. Wait, no, more? How many? How many variables? I think 12 summary variables. No, 24, because you have the mean and standard deviation, right? So you have 24 summary variables. Mean and standard deviation times 4 variables times 3 classes. So you have 24 summary variables to calculate. So you have the mean sepal length for class for Setosa, the standard deviation of, I can't even keep track of it, but you get it, right? See, there's 24 summary variables you have to calculate, and then you have each 3 likelihoods to calculate, and each likelihood is the product of 4 of these things, okay? And it feels like a lot of work, but yeah, I mean, you just, believe me. The naive Bayes classifier does make your life easier in that you don't have to worry about the variances, right? You don't have to worry about the variances. Okay, and that should work. And then R has a built-in naive, not a built-in, I think there's a package you load up. It has a naive Bayes classifier, and it should give you the same answers as what you program. And that always feels good, I think. Yes?
Just wondering, like, so if we're using this in practice and then also making an assumption that the data that we get is normally distributed, that even causes potentially more error, and then on top of using negative data. So it's like, how practical even is this model?
How practical is it? Yeah. In a lot of cases, it's okay enough that it works okay enough, right? So, yeah, when as far as like making predictions go, a lot of times it works good enough, even though we say like, is the data actually normally distributed? Probably not. Okay, but it's symmetric enough that we can kind of treat it as normally distributed. If you have like huge outliers and if it's like super skewed, maybe you want to do an adjustment, like take the square root of the number, and you might not be like, hey, what does it even mean to have square root of, of this thing, and that might not be normally distributed, but that might make it a little bit more symmetric, okay? Or take the log of it, and maybe that makes the data a little bit more symmetric. So there's a bunch of things, and there's a little bit of kind of this hack and slash trial and error to kind of get through the data to get your model to kind of work. And again, if somebody says defend all of your assumptions, you might have a little bit of a hard time, and you might just have to say, well, it performs well, and I hope that's good enough. And that might not pass a dissertation defense, but if you need to, you just want to make some predictions here, it might be okay, right? As long as you're aware of the assumptions you're making and you recognize the limitations and you don't say, well, here's the model and it worked before and therefore it's going to work forever. That should help you avoid getting in too much trouble. Okay, let me give you your second view quiz answer. Is the letter E. E as an elephant is our second view quiz answer. E. E as an elephant. All right, and so here's kind of I don't know if this is a fun application, a little bit of an application of using the naive Bayes classifier is you can use it as a document classifier. Okay, and I'm going to just run through a very, very, very simple, silly example. And it's like every example in this class is simple and silly. But we're going to use the naive Bayes classifier as a document classifier. And we like to use the naive Bayes classifier to classify documents because when we classify documents, the variables are going to be the count of each word, okay? And so if you think about the English language, I don't know how many words there are. 80,000? 100,000? I don't know. A lot, okay? Thousands of words, right? Even if you like simplify the English language and say, hey, let's only look at the top 10,000 words, okay? Sure, let's only look at the top 10,000 words. That's a lot of variables, okay? And how many covariances, right? Like what's the covariance between the words good and evil? Like how often do they show up in the same sentence, okay? And then you're like, oh, okay, well, they often contrast each other, so they show up quite a bit. But then it's like, okay, what about like, what's the covariance between, I don't know, microphone and door? And you're like, oh, I'm not quite sure. Maybe there's a relationship there or not. And then so you try to think of like, you pick two random words, right? Like today's Wordle answer and yesterday's Wordle answer. And what's the covariance between those things? And you're like, oh my gosh, there's so many covariances. And sure, certainly some words appear together frequently, okay? Like joy and happiness and stuff. We'd say, okay, those are semantically related and stuff. But then there's a whole bunch of other words that don't really have any kind of covariance between them. And then so if you wanted like a true model that didn't make the naive assumption, you have like a lot of covariances to estimate, and that's like too hard to do, right? So it's easier to just treat every word as appearing independently of each other, and we know that's not how languages work, okay? So we know that's not how it works, but it certainly makes our life easier, not having to worry about calculating these covariances, all right? And And so because you're going to treat all of these words as being independent of each other, this is effectively what we call a bag of words model. Okay? And the bag of words says a document can be treated as a bag of words. Okay? And the term document is a very loose thing. Basically, a single sentence can be a document. It could be a literal document like a newspaper article, it could be a Wikipedia article, but you can also say a tweet is a quote-unquote document, or a caption to a picture is a quote-unquote document, and all of those things. And the idea here is like, imagine this slide here as a document, and I'm like in an animation, a cartoon, like I shake the slide, and then the words just drop down and into like some jumble, and then now we treat this as like a bag, where it's just the words are jumbled up at the bottom. The order of the words don't matter, right? Once you put it in a bag, there's no order, right? When you say, give me this third item in your backpack, it's kind of a nonsense thing, because in your backpack, there's no ordering of the objects in there, right? So there are serious limitations to the bag of words model, right? If you have this document, it is bad, it is not good, right? The document gets turned into a count of words. You have two instances of it, two instances of is, bad one, not one, good one, okay? And then if you have this other document, it is good, it is not bad, you get the exact same vector of words, right? It to, is to, bad one, not one, good one, right? And so both of these documents, according to the bag of words model, have the same contents, have the same information, okay? Even though these two words or sentences or documents have exact opposite meanings, okay? And so a lot of times, like people want to do like sentiment analysis projects on tweets or something, which, by the way, it's like, okay, I don't know if anybody's have done this, and I don't want to like poo-poo on your project, but but it's like, I feel like if somebody proposes another Twitter sentiment analysis thing, it's like, oh gosh. And it's like using a bag of words model, it's not going to be good, okay? Because for sentiment analysis, right, these two sentences have exact opposite sentiments, or documents have exact opposite sentiments, but the bag of words model is going to treat them exactly the same, right? You'd have to at least go into like 2 grams or something. Okay, so anyway, major shortcoming in the bag of words model. Okay, but anyway, the way it's going to work, so shortcomings aside, all of these bad assumptions aside, the way the document classifier works is, first, it requires us to have a lexicon, which is basically a list of all the words that we're going to include in our calculations, and there has to be a probability associated with every single word, right? So there is, so the probabilities in a lexicon are usually really, really, really tiny, right? Like, what is the probability that the word, I don't know, keys shows up in any random sentence? And it's like, I don't know. It's probably on the order of like 10 to the minus 3 or 10 to the minus 4, you know, something really small. But here's just a very, very, very simple example lexicon. And I only have 8 words in my entire language here, okay? Or 8 words in my entire lexicon. And we're going to say there's 2 classifications, right? This lexicon can be used to decide whether a sentence or document is about a fairy tale or whether it's about chess, okay? And then so we're going to have the words king, queen, princess, knight, rook, good, evil, and bored, all right? And so we're going to say if it's about a fairy tale, what's the probability it has about it, something about a king? Okay, that's decent probability, 0.12. Queen, fairly high probability. Princess has a high probability. Knight have a high probability. These words show up in fairy tale stories. What about the word rook? Probably not so much in a fairy tale. Good, okay. And evil, sure. A board, not so much in a fairy tale, right? Okay, if we're talking about the board game chess, king and queen, sure, those will come up in a chess game. A princess in a chess game, not so much. Knight, yes. Rook, yes. Good, maybe, like we could talk about a good move, a good something. Okay, evil, it's a bit of a harsh judgment in the game of chess, right? So we're going to put a low probability on the word evil, right? And then bored, definitely there will be some discussion there, okay? So we're going to put, have these kind of things, right? And you could just imagine this being expanded greatly to, include like thousands of words and maybe hundreds of categories, right? If you're like a newspaper, you might have a bunch of articles and you might want to say this one's about politics and this one's about sports and this one's about health and science or whatever, right? And so you would train your lexicon, right? So I just made up these probabilities, okay? But you would actually do some training of a lexicon by like scanning all of these documents, and you would say, okay, well, we know these documents are about science, and therefore we're going to scan all of these things, and we know these documents are about, I don't know, politics, and we're going to scan all of the words, and you go through and you're going to create for each of these document classifications or categories, you're going to create a lexicon of probabilities for every word that you're interested in, okay? It's common practice to remove very common words, such as the, is, to, a. We often call these stop words because these often don't provide information as far as classifying a document. Okay, all right, and with the naive Bayes classifier, let's say this is our sentence. The evil queen sent the evil knight to capture the princess, okay? It's probably about a fairy tale, not about chess, okay? I suppose if we had, I don't know, the evil queen sent the evil knight to capture the other knight. Now it's a little ambiguous, and it's like, why are we personifying the chess pieces? I don't know, right? But here, there's a few, like, we look at this, and just this sentence, we're like, okay, probably a fairy tale, right? So anyway, using the bag of words model, we just take the count of the words that appear from our lexicon. So we say queen appears once, princess appears once, knight appears once, and evil appears twice, okay? Because they really wanted to emphasize that this was an evil thing going on, okay? So we're gonna say, okay, the likelihood, so I left off a bunch of calculations, but we're gonna say, what's the likelihood of our data given that it was from class fairy tale? So it's gonna be the probability of queen given fairy tale, princess given fairy tale, knight given fairy tale, and evil shows up twice, so we're gonna do evil given fairy tale squared, okay? So we go back to our table. Queen is 0.2, princess is 0.25, knight is 0.2, and evil is 0.11. And so we have this, and this calculation ends up being 0.000121. Okay, this is the likelihood of these words appearing. Okay, and again, the naive Bayes assumption allows us to just multiply all of these probabilities as if they were independent, and we don't worry about the covariances of how likely two words are to appear in the sentence together or things like that. Okay, we say, okay, well, what is the likelihood that this sentence is about chess? Okay, and if it's about chess, okay, we have the same counts, but our probabilities are different. Okay, queen has a probability of 0.2, but princess makes it much less likely to be about chess, 0.01. Knight has a decent probability, 0.15, but the word evil is unlikely to appear in chess discussions, and so we would have 0.01, and it appeared twice, so we're going to have 0.01 squared, and therefore the likelihood for this thing is going to be like 10 to the negative 8 times 3, okay, 0.000003. Okay, and I left off the last calculations to get the posterior probability, but basically you would take, whatever prior probabilities you had. Let's say if the prior probabilities were 0.5, like is it equally likely to be about a fairy tale or chess, then you multiply that to get your, the numerator, likelihood times the prior. You add them up to get your marginal. And basically, it's going to be like 99 point something percent fairy tale and close to 0% being about chess based on this sentence and these things, okay? And so The naive Bayes classifier is a popular choice for document classification. Again, what it requires is that you have known documents that are labeled, and you use those to create your lexicon of probabilities. Okay, any questions? All right, let me give you your last view quiz answer for today. The last view quiz answer is the letter A. A as in apple. A as in apple. All right, that will be it. And we'll end here, and we'll see you on Friday. And I guess I'll talk about the midterm exam then. All right, we'll see you.